Good afternoon, everyone. Online participant, are you able to see my screen?
Yes, sir.
Yeah, okay, thank you. So in this session, we will discuss about parallel algorithms. I'll also tell you some of the algorithms which we are using in cloud environment, which we can implement in using high performance computing. In fact, some of the algorithms started with high performance cluster computing, in which multiple processors are involved, and you have to take a decision that which processor is going to execute which particular task. For example, if you see this particular slide, I am showing you three different directed acyclic graph, or you can say it is a directed graph. So there are three different applications. We call this directed acyclic graph as an application. For example, if you see here, first one is application 1 that comprises of 5 different tasks. Second application is comprises of 4 different tasks. Third application comprises of 3 tasks. And these 3 applications arrived at a different period of time. Based on the requirement, they will arrive to the system, right? And we know in directed acyclic graph, for example, if you see the first one, until unless the execution of task A is completed, you cannot start task B and task C. Similarly, until unless the execution of B and C is completed, you cannot start E. So there is a dependency between tasks. We call this application as precedence constraint application. So I am showing you 3 different applications, and the arrival of these application to the system is different. Like you can see, application 1 arrived at time 0, whereas application 2 arrived at time 3, and application 3 arrived at the time of 9. Suppose you have 3 processors to execute. It is a multi-processor scheduling, right? Assume that you have 3 processors where you have to execute this set of applications. And another constant you can see, different applications are having different priority. Like if you see, first application is having priority, low priority. Third application is also a low priority application, and second application is a high priority application. The meaning of high priority, low priority here is that if you are executing a low priority application task, and if a high priority application task arrives to the system, then it can preempt it. For example, assume that task A is executing. At that time, task F is coming into your system, then F can preempt A. That's why application 2 is having more priority than application 1 and application 3. 1 and 3 is having same priority. Now, here I have written cloud 1, cloud 2, cloud 3, but we have 3 different machines. You assume that 3 different machines, or this is a multi-processor one. So first what you have to do, based upon the task size is generally represented in the form of instruction and data. So you have to estimate how much time it will take to execute in a particular machine. It is an estimation. For example, I am giving a rough picture here. We say that if task A is assigned to machine number 1, it will take 2 units of time. Anytime, you can say 2 milliseconds, 2 seconds, or you can say it is 2 hours. Some time unit is given to you. Similarly, but if task A is assigned to another machine, it is taking 3 units of time. If it is assigned to the third machine, it is taking 5 units of time. So what you can say, these processors or these machines are not identical. Is they are having different configurations, the time is different. So we call this a heterogeneous system. That's why it is taking different unit of time in different processes. Like that, you can see for other tasks also, some rough estimation is given to you, in which you have to decide which task you have to schedule first. Okay. At the same time, you have to also see the precedence constant. You cannot execute task B and C prior to A, because there is a dependency. Once B and C is completed, then only you can go for D and E. Right? And D is dependent on B only, but E is dependent on B and C. Right? So now you have to design that you have to develop a scheduling algorithm to process these applications based on their arrival to the system, because you know arrival time of applications are also I mentioned 0, 3, 9. Also, you need to focus on what is there in a particular application, what is the constant, right? A followed by B and C. Okay. So, for example, you know, in any scheduling algorithm, first we try with the baseline algorithm. Baseline algorithm means you can apply first in first out, or you can go for round robin algorithm. So people have tried to implement the same set of application in round robin. Okay. What is the rule of round robin? Round robin says that equally you have to distribute, right? So round robin assigned A to the first processor, B to the second processor, C to the third processor. When D is coming, it is assigned to processor number 1. Because we have only 3 processors. Once the cycle is completed, you have to again start that particular cycle, right? Similarly, D is assigned to the first one, E is assigned to the second one. When you change a particular application, like this is application 1, this is application 2. So A file assigned to processor 1, G file assigned to processor 2, H to processor 3, and I to again processor 1. Right? You can see this sequence, whatever I have written. Okay. Edge case, sorry, third application case, J will go to the first processor, K will go to the second processor, L will go to the third. So in this way, you have to process in the round. Although you have given a particular order, for example, if you look into the processor number 1, it is getting A, processor number 2 is getting B, processor number 3 is getting C, but they cannot execute simultaneously. Okay? ABC cannot be executed simultaneously. What is the reason? The reason is that B and C are dependent on A. Right? Until unless A is completed, you cannot start B and C. Okay. So while you are determining the round robin order, this matrix which I have calculated, we call this matrix as expected time to complete matrix, ETC matrix. In high performance cluster computing, we call this is a expected time to complete matrix. Right? Do we need this particular machine, table or matrix for executing in RF? No. Do we need this one? You have already a predetermined order, right? 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, like that, right? So there is no need of this particular matrix. So importance of this matrix is not there in the round. That's why when you process multiple applications, so you will see the performance of round robin is very poor. So what literature suggested? We'll check, like if you talk about task A, so it is taking 2, 3, and 5, right? 2, 3, 5 in 3 different machines. So you have to choose the minimum one. Obviously, a particular machine is taking less time, so we are ready about time, so we'll go for that, right? Similarly, can you tell me for B which machine I'll choose? First machine or second machine or third machine? If it is 684, we'll go to the third machine, right? Similarly, C case, I'll go for second machine and so on. So this scheduling is called release scheduling, which is a very popular scheduling algorithm. So any algorithm you can develop in your career related to HPC, first you have to compare with these two algorithms because these are said to be the baseline algorithms. But again, there is a drawback in the least scheduling. What is the drawback? Like you can see, if you take this example, for example, for B, you told that machine 3 is best. For D also machine 3 is best. I don't know. For B also machine 3 is best. This particular D also gets machine 3 is best. So while you are assigning D to that particular machine, you are not considering B is already allocated to that particular machine. So which we call as ready time. Okay. So you have to consider prior time also. Like somebody, you have given some work to a person who is busy for let's say 5 hours. Still you are assigning the task. That person will execute after 5 hours only. So before assigning that, you need to consider the ready time. Not only execution time is important, but also ready time is required, right? So in order to calculate the completion time of a particular task in a machine, we need to consider ready time and execution. That's why completion time is equal to execution time plus ready. Why I am showing you this application? I'll show you here. If you go for, there are many scientific applications. Like here you can see one of the application that is called as montage. Another application, epigenomics. another is SIPST. These are realistic applications that is used in the field of biology, used in the field of gravitational physics, used in the field of earthquake also. So when you are given with such type of application, processing in high performance computing is very challenging. Because not only you are considering computation time, but also you need to consider communication time. Like you can see, these four tasks are the root tasks, right? They are not dependent on anyone, so they can execute simultaneously. But once it is completed, you can start the next six tasks based on their dependency. But you can see the second level, like this particular task, if you see, there is so many dependencies. It is not only dependent on a particular task, it is dependent on more than one task. That is a communication time. Maybe this particular task completed early, it has sent the result to this particular machine with this particular task, but other task is not sent the result in, because it is taking more time. So you have to wait until unless you will get result of all the tasks which you are dependent, you cannot start your task. So in order to generate it, there is two ways. You can either go for the standard realistic applications which is used in the respective field, which I mentioned here. And I am showing you these three. LIGO is also used in gravitational physics, SIPS is used in the biology. So if such a application is given to you, so you have to execute this application in such a manner that overall completion time is minimized. Okay. Overall completion time we call that is called as a max time. So max time you need to minimize in order to process an application. On the other hand, what you can do, if you don't want to use this realistic application, design a random directed acyclic graph generator. You can generate a random graph. You generate the computation time and communication time executing multiple machines. Right? And then I have to use the realistic workflows, or I have to generate different random graphs. In that random graphs, what I do, I generate the computation time as well as communication time, and I'll see what is the time required to process in multi-process system. So I'll tell you a very simple example so that you can understand. Okay, this is LIGO and CyberSec. You can see structure of these applications are different. Okay, structure of these applications are completely different. So take an example of a single application. Okay, so here I am showing you 6 different tasks, and you can see there is a value I have written within the node, and there is a value I have written between two nodes. So the time which I mentioned within a particular node, that is called as computation time. And the time required from moving from here to here, it is 4 units of time. That is called as communication time. But in HPC system, when we write the algorithm, when we develop an algorithm, we assume that if parent is assigned to X processor and child is also assigned to X processor, the communication time is negligible. Right? Suppose I am assigning T1 to processor X, T2 to also processor X. So once T1 is completed, the result will come to T2. So as both parent and child is assigned to the same processor, the communication time is assumed to be negligible. Otherwise, you have to wait 4 units of time before you start the thing. Right? So how to process this application? The challenging problem is that you have to process the 6 tasks by respecting their precedence constraint, such that overall completion time is minimized. Okay. So I am talking about a single graph. Assume that we have multiple graphs. Right? I am starting with a single graph. You have multiple graphs. Again, priority of the application is also different. So there are many delay sensitive applications there, many machine critical applications are there. So you have to process them before non-sensitive application. Like you are browsing a YouTube video, if it is delayed little bit, nothing is going to happen. But when we talk about real-time system, like airline system, if something is happened, then it leads to a catastrophic event. So you have to see the sensitivity, okay, or sensitiveness of a particular application. Okay. So in order to solve this problem, in the literature, people have come up with various parameters. The first one they are using, that is called as T level. Okay. So generally these algorithms are started in the field of cluster. Later they are used in the grid. Then now we are using in the field of cloud. So T level is also called as soon as possible. So you have to calculate ASAP, as soon as possible, or T level of all the 6 tasks. Okay. How to calculate it? That I'll tell you. So T level is defined as it is a path from entry task to a given task Ti. Which one is entry task here? For all the tasks, entry task is T1 only. So when you calculate T level of T1, then entry task is T1, given task is also T1. But when you take T2, entry task is T1, given task is T2. What you are determining? You are determining a path. Based on that path, what you will do? You will calculate as soon as possible. So a path contains what? A path contains 2 things. One is computation time, and another is communication time. So what T level suggests here, that you need to consider both computation time and communication time when you traverse from entry task to given task. Right? So that is based on that you can calculate T level. And you can see in this graph also, okay, directed acyclic graph, there are multiple paths exist. For example, if I say T3, so somebody can say that I can move from T1 to T3, or there is a path from T1, T2, then T3. That is also another path. Right or not? There is a direct path, there is another path is also. So which path you will choose? For that, if there is more than one path exists, you have to select the maximum path. Okay. So this is T level calculation. For example, if you go for T1, what is the T level? Can anybody calculate? T1 to T1, what is the cost? 0? 0. T1 to T1, it is 0. So you can see here, all computation and communication cost we are calculating, except the computation cost of given task. So for T1, entry task is T1, given task is T1, and you are ignoring the computation cost of T1. It is 0. So T level of always the entry task is 0. Is it clear? Now coming to T2. What is the T level of T2? See here. In order to reach T2, how many paths exist? 1. So what is the time? 5 plus 4. I am not going to calculate the computation time of given task. So T level is 9. Now take T3. If I take T3, I have a direct path, so it is 5 plus 3. Or if I go this way, 5 plus 4 plus 7 plus 12. So I am getting 2 different paths. So if you take 2 paths, you will get 8 and 20. But what I told you, you have to choose. If there are more than one path exists, you have to choose the maximum path. Okay. Like that, I think you can calculate what is the T level of the entire application. That is not the end of the story. Once you can calculate T level, it is challenging for you. What? You have to assign to the processors. If you have multiple processors, why maximum? That is as soon as possible. Okay, it may delay, right? For example, somebody will tell, like we called 2 persons to go for a restaurant, right? First person is saying, I'll come. Second person is saying also, I'll come. One person reached after 5 minutes. Another person is coming after 20 minutes. So your journey will start after 20 minutes, right? In the similar way, although one task is completed that is providing you result, but you have to wait for another part, right? That's why we are taking the maximum. So if I execute in a 2 processor system, you think about, suppose you are given with the 2 processors to execute this application. So there is a multi-processor scheduling, right? So what you will do? You have to assign the task in the non-increasing order of T level. Okay. What is non-increasing order? Why not increasing order? Increasing order means 1, 2, 3, 4, 5 is increasing order. But if it is 1, 2, 2, 3, 4, 2, 2, 2 case, both 2, 2 case, you are not increasing. But you are not decreasing. That's why I'm saying non-increasing order. So if you look into this one, especially look into the which I have given in bold color. So I'll start T1. Okay, T1 is having least T level. Then I'll go for T2. Then I'll go for T4. right? Then I'll go for T5, then I'll go for T3, then I'll go for T6. So this order you have to follow, but again you have to see the precedence constant of the task. Not necessarily you will follow this order. Sometimes what happens, I'll tell a real life example. For example, we know that the Tatkal time is 10 am. Right? We know Tatkal time is 10 am. So for Tatkal, if you go to the counter, right, railway reservation counter, we reach the counter in night time. Right? If you want to really book a ticket, you have to reach night time. So suppose somebody arrived in morning 6. Okay? Assume that the queue is empty. So that person has to make a queue from 6 am to 10 am. So his request will be solved at what? 10 am. But he should not obstruct the people who can book the ticket from 6 am to 10 am. Right or not? If we block the counter, nobody can book the ticket from 6 to 10 am, right? That's why those people who are coming late also, if their request can be solved before 10 am, we'll allow them. That is the concept of back patching. Okay. We allow other people because resource is available and it is not hampering others, we can execute it. Similarly, whatever order I have mentioned, you can violate the order if one task is dependent and waiting when other task is ready. So in cluster computing or high performance cluster computing, we call this the insertion approach or non-insertion approach. Whether you are allowing it or you are not allowing. Based on that also different type of scheduling algorithms are developed. Okay. Now, if I tell you to solve this problem using a two-process system, what you will do? First, you will execute T1 in processor 1. So what T2 will do that time? Sorry, processor 2, what it will do? If a particular processor is executing T1, what other processor will do? It is sitting idle. Right? It is sitting idle or not? It is not doing any task. Because I cannot start T2 and T4 or T2 or T4. It is not possible to start until unless T1 is completed. Right or not? So there is a concept in the scheduling that is called the replication. Wherever it is possible, you do the replication. Replication meaning means T1 will execute in processor 1. T1 is also executing processor 2. What advantages you will get? So once T1 is completed, you can start T2. On the other hand, if T4 is ready, you can start T4. But as T1 is executed in only one processor, suppose assume that only one processor, that processor has to send the result to second processor, which takes time. But when I do replication of T1, both T2 and T4 can execute in two processors because their parent is available, parent's results is available. So in that case, you can reduce the communication time of a particular application. Okay, that is the replication strategy people have used to assign it to a multiprocessor schedule. Not only this is important, T level, there is another thing is called as B level. Bottom level. These are different approaches. Like he mentioned that why you are taking maximum one, why not minimum one. So there are various performance practices people have developed. Okay, and they check that which case it is performing better. Different algorithm follows different type of levels to execute the application. Okay, what bottom level says? It is a path from a given task Ti to the exit task. Okay, the name suggests top level means what? Entry to the given task. Bottom level means given task to the exit task. You know whether it is an entry task or an exit task, that is already fixed for a particular application. So if you look into this application, when you take T1, your exit task is T6. If you take T5, your exit task is T6. For all tasks, exit task is T6. What you are determining? You are determining a path from one task, one given task to the exit task. Right? So if you see T1 to T6, there are multiple paths out there. Right? You can come T1, T2, T5, T6. That is one path. T1, T2, T3, T6. That is another path. T1, T3, T6 another path. T1, T4, T5, T6 one path. T1, T4, T6 another path. So you have to calculate all possible paths. Now, what about computation time and communication time? B level suggested that you will take only the computation cost. You are not going to consider communication cost. That's why I told you in my previous lecture also. Sometimes computation is dominating communication. Sometimes communication is dominating the computation. That's why we calculate this ratio, computation to communication ratio in parallel system. Okay, that is having significance, right? So in this case, if you see computation cost, why we are focusing on computation, not in communication? We assume that communication is negligible. Like I am doing 23 hours of processing, and let's say transferring the data, communication takes only 5 minutes. So in comparison to this 23 hours, 5 minutes is negligible, right? So can you calculate for, let's say you calculate for T5, can you calculate for T5 to T6 B level of T5? What is the B level of T5? Hmm? It includes only computation cost. Okay. So some case you are taking computation time, some case you are taking communication time. It says that you have to calculate, you have to take computation cost of the exit task also. So it is not ignoring communication cost. Next performance metrics, you are ignoring the communication cost. So it is 2, it is 5, and it is 8. Right? So it is 15. So what is the B level of T5? It is 15. So in the previous case, if you remember, when you calculate entry task to the given task, you are ignoring the computation time of the given task. But now you are taking given task to the exit task, you are including the computation time of the exit task. That's the only difference. Similarly, if I say T4, you can say 4 plus 11 plus 8. This is the time. How much you will get? 15 plus 8, 23. Or you can go for 4, then 9, 13, 2, 15, 5, 20 plus 8, 28. So you will get 28 and 23. You will choose the maximum. That is another type of matrix. And once you determine these particular values, what you will do? Choose a task is having this, choose a task with the maximum B level. Like if you see here, who is having maximum B level? T1. So T1 we assign first, followed by T2, then T4, then T3, T5 in any order. That's why I told you non-increasing order. Okay, in this case, non-decreasing order. 15 and 15. So there is a tie. You can execute T3 followed by T5 or T5 followed by T3. Okay, then you will execute it. So that is another type of processing. Next is the static bottom level. This is another type of matrix. We call that as a static level. How to calculate static level? It is a path from a given task Ti to exit task. Given task to Ti to exit, or Ti to the exit task. So we are taking exit task. Exit task means it is same as your B level, but it says that it is only taking the computation cost. We are not going to include the communication cost. Right? We are not calculating the communication cost. We are only considering the computation cost. So let us calculate it. For example, let us go for T5. T5 is my given task. T6 is my exit task. So T5 to T6 you will determine the path. So you will include only computation time. So 2 plus 8, you will get 10. Is it correct? Similarly, if you go for T4, if I take computation time, it is 4 and it is 8. So it is 12. If you go this particular path, it is 4 plus 2 plus 8. Okay, so it is 14. So you will get two solutions, 14 and 12. And here also we are choosing the maximum. Okay. Now coming to another one that is called as late as possible. As late as possible means how much time you can defer the execution. Right. So in order to find ALAP, first you have to determine the critical path. I think all of you know what is a critical path. Critical path is the maximum path from source to the destination or entry to the exit task. Right? You will go for all possible paths, find the maximum path. Okay. So once you determine the critical path, you have to subtract this part from the critical path. What you have to do? You have to do backtracking. So starting with exit task to a given task. Has to determine the critical path. Critical path is same for all. Irrespective of the task, the critical path is same. Then in that, then what you have to do? You have to subtract with this part. That is the path from exit task to a given task. For example, For all the tasks, what is our critical path? 43, right? Now, if you go for T6, okay, T6 computation time is 8. What I said here, exit task to the given task. Exit task to the given task. Exit task is T6. Given task is also T6, right? So, if you take here, that is -8. So 43 minus 8, you will get 34. Right? Similarly, if you take T5, 43 minus 8 plus 5 plus 2. So it is 15. Right? 43 minus 15, you will get 20. And all of the tasks based on the least ALAP. Okay, so you will find the order T1 followed by T2. Okay, then followed by T4, then T3, T5. There is a tie, so you can follow in any order. Then you go for T6. Okay, so in this way, you have to assign a particular order if you are dealing with more processes. And we have also seen increasing the number of processors. It is not going to increase the performance. Right? It purely depends upon the application. Right? For example, here, if you see how many maximum processors are required to execute this particular application. Maximum how many processors are required? Let's say 3. Okay, based on this application, it is 3. Suppose you are available with you have I will make it available with for you 100 processors. So beyond a particular limit, okay, your performance is not going to be. That's why selecting the minimum number of processors to execute a particular application is also a challenging. Right? Not only we have to look into the width to determine that how many processors are required. Not only we'll see this width, like this width is 3, that's why we take 3 processors. It may happen that while you are executing this one, these two finish their execution. Still you can manage with 2 processors. Okay, that's why you need to consider these factors before assigning any task or any application to the processors. Right? We should not waste the cycles of our processors, right? So minimum number of processors required, because if you go to the cloud, per processor you have to pay. Right? I told you in Amazon, right? If you take 10 virtual CPUs, you pay accordingly. If you take 100 virtual CPUs, you will pay accordingly, right? So you have to look into the minimum number of processors, and you have to ensure that it is not over provisioning. At the same time, it is not under provisioning. Okay. So these are I am talking about is a single application, right? But initially I told you you have to deal with the multiple applications. These multiple applications are having their priority also, and they arrived at a different period of time, and you have to apply a particular algorithm. So think about this complex environment, how to execute, right? And you have to consider all sorts of communications and computation costs in order to calculate the overall completion time. So now there are many. If you go to our scheduling part, you can find there are many type of scheduling algorithms that are developed for independent tasks. Okay, here we are talking about dependent tasks. You have dependency, right? Sometimes we are given a set of tasks which we call it a meta task. The set of tasks is called as meta task. Meta task means all the tasks are dependent on each other. So how to process a set of tasks? Suppose you have 10 tasks. How to process? Somebody will say we'll go one particular order, first in, first out order. There is also a solution. It will be a good solution, but it's the simplest solution, right? We'll execute one by one task and we'll finish our execution. So if you go for independent tasks, right? So you can categorize the independent task into independent task scheduling algorithm into 2 parts. You can go for either online scheduling or you can go for offline. So offline case, you have idea of all the tasks. Like in the previous this case, you have idea of everything, right? That's why you are able to calculate. Suppose I'll say only you have idea for T1, right? Once you execute T1, you will come to know that there is another 2 tasks available in your system. That is the online scheduling algorithm. When you take a static scenario, you have information. But when you take a dynamic situation, when you execute a root task, you don't have any information of other tasks. So taking designing a scheduling algorithm process it also challenge, right? So independent tasks can be processed in a particular sequence, right? For example, I have T1, T2, T3 up to T10, 10 tasks. So I will execute T1, then only I have information about T2. Once you complete T2, you have information about T3. So in this case, it is called as an online algorithm, right? You don't have an idea of all, how 10 tasks is there in the system or 100 tasks is there in the system. You don't have an idea. But when you go for offline scheduling, batch of task is given to you. You have to process it. Right? Batch of task is given to you. On the other hand, you have multiple processors are available. So in that case, the order can be changed. If 10 tasks is there, I can change the order if it is offline. I can execute T7 first, T5 second, T1 third. Based on some algorithm, I can decide that in which order I am going to process. That we can do, right? So if you come to the independent scheduling in cluster computing perspective, people have developed so many algorithms. Okay, or lead case also there are so many algorithms are. One of the popular algorithm is called as opportunistic load balancing. Okay, so this algorithm is also called as this is also OLB is also called as some assignment algorithms also. It is a very simplest algorithm. So let us see one example so that you can understand. For example, you have three machines. Assume that these three machines are busy for some amount of time, which we call as ready time. In cloud case, we call as cloud ready time. For example, the task or local task which is assigned to a particular machine, it is busy, it is next busy that particular machine for 89 unit of time. Whatever task assigned to the second machine, it is busy for 73 unit of time. And whatever task is assigned to the third machine, it is busy for 50 unit of time. Now we go one by one task. It is the online one. Online one means when you assign T1, you don't have any idea of T2 to T5. When you assign T2, you don't have idea of T3 to T5. Now, in what order you will assign so that overall completion time to execute these 5 applications or 5 tasks is minimum. That you have to look at, right? So, can you tell me which machine is going to be free fast out of these 3 machines? If it is busy for 89, 73, 50 times of units of time, which machine will free fast? First machine or second machine or third machine? Assume that 3 machine is there. First machine is going to be going to solve a particular request after 89 unit of time. Second machine is 73 unit of time. Third machine 50 unit of time. Which machine is going to ready first? 50 unit of time, right? So that's why T1 is assigned to that particular machine, right? We have estimated the time for T1 in 3 different machines, but finally we have assigned to C3. The reason is that that machine is going to be free fast. But unfortunately, you can see here 70, 80, 108. Which one is minimum? The minimum is 70. Although that is minimum, but the strategy says that you have to choose a machine which is ready first. Right? So once you assign T1 to the machine number 3, so you will update again the ready time. What is the updated time? 89 is as it is because we have not assigned anything to machine 1. 73 in the second machine. In the third machine, earlier the ready time is 50, but as you have assigned T1, so it is 50 plus 108. Is it clear? So I have updated the ready time. Right? Now when T2 is coming into the picture, I'll ask you by looking into the statistics, tell me which machine is going to ready first? 73, right? It is the second machine. So irrespective of these values, what I will do? I'll assign to which machine is ready first. Okay, I have written here, sorry. Okay, second machine. Right? And fortunately, that is the maybe that best second best machine. Sorry, this is the best machine, right? Is it clear how we are proceeding? Right? Then you again updated the ready time. Then for T3 again you choose which one is best. Okay. Although C3 is best, but based on our ready time, which one is best? 89. So we assign T3 to the first machine. What is the comparison here? For each task, okay, Anyhow, if you go for a complexity, you will find order of m. If there are n number of machines are there, because you have to look each and every machine's ready time. If there are m machines are there, m ready time is there. Until unless you scan n number of machines, it is not possible to determine which one is minimum. Right or not? So the complexity required to assign a particular task is order of m. If you take n number of tasks, complexity is nn. For task, it is order of n. For n number of tasks, the complexity is order of n. Right? So this is one of the oldest scheduling algorithm. Let us come to another algorithm which improves the performance of OS. That is called as opportunistic. In order to avoid the demerit of opportunistic load balancing, we are using another algorithm that is called minimum execution time. What minimum execution time says? Not only the ready time is important. Instead of the ready time, you choose the machine which takes less time. That is only called minimum execution time. So let us see one example. So for example, assume that there is no ready time. Assume that ready time is not given to you. So ready time is considered as 0, or assume that if you have 4 machines or 4 processors, all the processors are idle. They are not doing any task. So for T1, you have estimated what is the estimated time to execute in 4 machines. So you found that which machine is best? First machine. So you are assigning the task T1 to the first machine. Now, if you come to T2, we have estimated the time in 4 different processors. It is 74, 105, 81, and 93. Which one is best? Again 74, that is the first machine. You go to the third task, which one is best? First machine. You go to the fourth, which one is best? First machine. So, all the tasks are assigned to which machine? First machine. It is having a load balancing issue. Right? Load balancing concept says that you have to equally distribute the load. But you try to assign based on the minimum execution time. Finally, it is not the load balanced one. Right? So the make S1 you can calculate. Make S1 is the overall completion time. The overall completion time to execute this 4 tasks is 178. Okay, where of the other 3 processes are completely idle. So that is not a efficient algorithm. You may say that why you have selected these values like this. You may ask, right? I have intentionally taken the base machine is the first machine. So there is a benchmark. I'll show you first that benchmark, then we discuss. So there is a data set. The data set comprises of 12 instances. And the data set size is 512 into 16. What is 512? 512 means there are 512 number of tasks is there. 16 number of machines we have. So total metric size is 512 into 16. Okay. Similarly, there is a data set that is 1024 tasks with 24 machines. Sorry, 1024 tasks with 32 machines. One is 512 into 16 machine, where 512 tasks you need to assign to 16 different processors. Another case, 1024 tasks you have to assign to 32 machines. 2048 tasks to 64 machines. 4096 into 128 machines. So you decide whether your system is capable to execute this type of this many number of tasks. Based on that, you can assess it. But irrespective of the size of the file, okay, whether it is 512 into 16 or 102432, you will find 12 different instances. So you can see in the instances, all the, if you see the first letter, what is the first letter? U. What is U? U stands for uniform distribution. In mathematics, we have studied different types of distribution. So to generate this particular data set, it is a benchmark data set. It is not a normal data set. It is a benchmark data set. If you develop any algorithm in high performance cluster computing or now in cloud computing, you have to compare your algorithm with these benchmarks. So U says that the uniform distribution is used to generate this particular data set. Okay. There are other distributions are there. Binomial distribution is there. Poissian distribution is there. Okay. You can apply that also to generate a particular data set. Because you cannot fix a particular value. Like I told you in MET case, for this example, I have taken the minimum value first. It is a biased one, right? You cannot guarantee that everywhere one machine is always best, right? So I think U is clear, right? What is the next letter? C and I and S. C stands for consistent, I stands for inconsistent, S stands for semi-consistent. What is consistent? Consistent means it is a steady state, right? Consistent means if a particular processor is best for a particular task, it is best for all the tasks, which we have seen in the case of ML. So they have generated 4 different instances, which is consistent. So if you found that processor 5 is best for one particular task, it is best for all the tasks. Okay. Next is inconsistent. Inconsistent means you cannot say which machine is best. First case maybe machine 1 is best, second case machine 5 is best, another case let's say machine 15 is best, and so on. That is called as inconsistent data sets. It's an inconsistent instances. Okay, so there is 4 inconsistent instances. Similarly, we have another thing that is called as semi-consistent. What is semi-consistent? If you take an inconsistent instance, okay, in that inconsistent instance, suppose it is a 512 into 16 instance. 512 number of tasks assigned to 16 machines. You found that a part of the matrix is consistent. If you take a 5 cross 5 matrix, and if you found that 3 cross 3 matrix is consistent, you find some peculiarity in that particular matrix. That type of observation is done in a semi-consistent matrix. Okay. What is the next value here? In the data set, after next to C, I, and S, HI. Right? We have HI, LO, HI, and LO. What is that? First one indicates a task heterogeneity. Second one indicates a machine heterogeneity. Okay. First one HI indicates task heterogeneity. So in this data set, task heterogeneity is high, machine heterogeneity is also high. So you will get a very big value. The computation time is very high. If you open this data set, you will see there is a 6 digits or 7 digit value. But when you go for high low, task heterogeneity is high, machine heterogeneity is low. Like you can categorize the task into small tasks, medium tasks, and large tasks. That we have seen if you go for IoT or fog and cloud architecture. IoT can do tiny tasks. It cannot execute large tasks. Fog can do a little bit bigger task than IoT device. And cloud can do any machine amount of tasks also it can process it, right? And you can see LO. Sorry, before that LO HI is there. So task heterogeneity is low, machine heterogeneity is high, and low case both heterogeneity is low. So if you open the 4th data set, you will get a 1-digit value or 2-digit value. Right? So whenever you are implementing any kind of multiprocess scheduling algorithm, okay, so you have to compare with these data sets. Okay, and .o stands for object file. Okay, so these are the data sets. So we usually compare with 512 into 16 up to 2048. You have not tried with 4096 because when you execute in real environment, it is really challenging, right? Okay, so we have seen one algorithm. I will go for the next algorithm. So we have seen MET algorithm in which a particular machine is best compared to other machines. So there is another algorithm that is called as MCT. I told you not only ready time is best required, but also you need what? Execution time. Both are important. Right? OLB deals with what? Ready time. MET deals with what? Execution time. Not only ready time is important, but also execution time is important. That's why completion time is calculated as execution time plus ready time. So let us see how to do this one using an example. So I'm taking the same example which you have seen in the case of MET. Now, initially, suppose I am assuming that the ready time is 0, means all the processors are free. Okay, all the processors are free. So now, you tell me, what is the completion time of T1 in C1? 20 is the execution time, 0 is the ready time. So completion time is execution time plus ready time. So execution time is 20. Ready time is 0. So completion time is 20. Similarly, if you calculate for C2, C3, C4, you will get the same. What you calculate? Obviously, ready time is 0 means computation time is same as Execution time is same as completion time. So now interesting thing will come when you go to T2. Okay, so I have assigned T1 to C1 based on the minimum completion time. Earlier you are assigning with minimum execution time. Now you are assigning with minimum completion time. As ready time is 0, you are not able to identify the difference. Right? Now come to T2. Here you will get the details. Now what is the execution time of T2? What is the execution time of T2 in first machine? 74. What is the ready time? Why ready time is 20? Because T1 is already assigned to C1. So C1 has to execute it, that machine has to execute it, right? So it is 20 and this one is 74. So now completion time is 94. Right? Somebody is saying that you wait 5 minutes, you will go. When you go, let's say you require 1 hour time. Right? Suppose now the time is let's say 1 p.m. Somebody is asking that you wait for 5 minutes. So your journey will start from 1:05. If you require 1 hour, it will complete by 2:05. Right or not? So, but when you calculate completion time in C2, C3, C4, is there any change? C2, C3, C4. What is the completion time in C2, C3, C4? Same as 105, 81 and 93 because you are not assigned any task to processor 2, processor 3 and processor 4. Is it clear or not? So now, once you calculate the completion time, you choose the minimum completion time. Which one is minimum completion time here? This is 94. This is 105, 81 and 93. It is C3, that is 81. So you are going to assign to the third processor. But what we did in MET case, we assigned to the first processor because we are not looking into the weight. Right? Similarly, one more we'll see. T3 case. These are the execution time. But what is the ready time? The ready time is in the first processor is 20. Ready time in the third processor is 81. Rest is as it is. Rest is as it is. Right? So, if you calculate the minimum completion time, you will find it 3. Right? Similarly, if you process based on the minimum completion time, you will get better result than other algorithms. That's why in the literature, MCP is considered as the benchmark algorithm for all type of online signaling. If you want to develop any kind of online signaling algorithm, first you need to compare with the MCP, whether the result is good. Okay. So for example, if you go to this data set, here I have highlighted something you can see. So this is the MCP column. So out of these 12 instances, how many instances MCP is performing better? 1, 2, 3, 4, 5, 6, 7. More than 50% of the instances you will get MCP is a better. Okay. But you can see other developments also people have done in the field of HPC, where they have applied a K% work based is one algorithm. Switching is another algorithm. And they found that KPB case, they also got 50%. In 6 instances, he is having better result. Sometimes it is a tie between MCT and KPB. You can see in this particular instance, like UI, low, high, both are getting the same result. Okay, so let us see one algorithm. This is one of these algorithms so that your idea is more clear. Okay, so there is another algorithm, like I mentioned, that is called as K% based. So you have to determine the value of K. Like machine learning, you have to know there is an algorithm called KNN, or K means clustering, right? You have to determine the value of K. And determining the actual value of K is always a challenging, right? It is not possible to predict the exact value of K for a particular application. So what it says, K% based, it is saying you should not check with all the machines. It is not required to check with all the available machines in multiprocessor scheduling. You have to select only K% machine. Suppose K is 50% and number of processor is 4. So how many machines you are going to choose? 2. Number of machine is 4, but my K% is 50%. So I will choose only 2. Okay. And if K is equal to, let's say, number of processor is 3 and K value is 67%, you will choose 2. So no need to map with all the machines. You have to choose only 2 best machines. There only you have to do the calculation. And K value is always determined in between 100 divided by M, where M is the number with the 100. Right? So when K value is equal to 100, you see there is a less than equal to, right? K value may be equal to 100 or K value may be equal to 100 divided by M. Right? So when K is equal to 100, KPB heuristic is same as your MCT heuristic. MCT means minimum completion time. But when you take K value as 100 divided by M here, so KPB is acting like a MET heuristic. So what you are doing? You are designing a hybrid algorithm by taking MET as well as MCT. Okay, you are taking MET as well as MCT. So if you are close towards 100 divided by M, more or less you are applying MET. If you are close towards 100, you are applying MCT. So now let us see what we will do. For example, for task T1, I am taking the same example as MET and MCT. So now, like if you go for consistent data set, which I told you, right? In consistent data set, you know which machine is best. You can also determine which machine is the second best. Okay, so you will concentrate on 2 machines only. So in this case, we have 4 different machines. As K is equal to 50%, we are taking only 2 machines. If K is 50%, if K is 100%, you will take all the 4 machines. All the 4 machines means it acts like a MCT. Right? But if you take K value is in between MET and MCT, so you have to choose an appropriate way. So in consistent machines, it is easy to find which 2 machine is best because there is no fluctuation. But inconsistent matrix, it is really challenging to choose the best machine, best 2 machine. Right? Or because for every task you will find a different machine. So for example, T1, if you see, look into this execution time, you will find the first machine and third machine is the best 2 machine. First machine and third machine is the best 2 machine. Other 2 machines are taking more time. So what we will do? You choose 2 machine, calculate the completion time. So in this case, completion time is same as execution time because ready time is 0. Right? That's why T1 is assigned to C1. What actually we want? We want to reduce the number of matchings. Here we are matching with all processors. So complexity is order of M. So if you want to match a subset of processors, complexity is reduced. Because in a practical system, you have so many number of processors, like top 500 or towards the website you have this seen. It is not practically possible to check with each machine. Right? So if you go for T2, right, the best 2 machine is C1 and C3. If you look into execution time, the best 2 machine is C1 and C3. What you have to do? You have to calculate the completion time. This is the execution time. Execution time wise, you have shortlisted 2 machines. Right? Now what you have to do? You have to calculate the completion time. But you have already assigned 1 task to C1. So its time is updated to 94. Whereas there is no task assigned to C3. That's why it is 81 plus 0, 80. Right? Now you tell me which machine you are going to assign. Which machine you are going to assign? Based on the minimum completion time. This is 81. Right? Because this is 94. Is it clear? Now coming to T3. Which 2 machines are best here? First machine and last machine, 33 and 40. Right? 58, 87 is more. So out of these 2 machines, which machine I'll assign? That depends upon the ready time. So it is 33 plus 20, whereas it is 40 plus 0. So it is coming 53, it is coming 40. So I am going to assign to which one? The last machine. So in this way, KPB is assigning to the machine. And through experimentation, if you go to there, you can find through experimentation, they found that K value is 20. It is not possible. If you change the data set, I cannot tell that K is equal to 20% will work for me. If you change the distribution, instead of taking uniform distribution, if you are generating the data in another distribution, there is no guarantee that whether K is equal to 20% will work for you. It is purely experiment basis. They have tried all possible values of k, or some shortlisted some range, let it be 20% to 60%, something like that. In the tested, in they found that 20% case they are getting the best. But there is no such type of threshold in MET or NCT or OLB. Okay. Although they have improved some cases, like you can see this particular case, UI high low. So in this case, what you can see, KPB is performing better than the NCT, right? But most of the cases still NCT is leading. That's why I told you the region benchmark algorithm. Whenever you are developing any kind of algorithm, go for NCT. If it is an independent task. Okay, the last algorithm that is called as SA. SA is a switching algorithm. It is again a hybrid algorithm between MET and NCT. A lot many algorithms are developed to make a trade-off between MET and MCT. Okay, so what it do? The SA algorithm, it is taking the maximum ready time and minimum ready time. Okay, it is calculating two things. One is maximum ready time, another is minimum ready time. Let us take maximum ready time as R max. R max indicates maximum ready time. R min indicates minimum ready time. And it is calculating a load balance index, which is represented as phi. Phi is equal to R min divided by R max. Phi is what? Load balance index. Okay. How you calculate load balance index? It is based on minimum. It is based on minimum ready time divided by maximum ready. Okay. Minimum ready time you have to divide with maximum ready time. You have to calculate load balance index, and you have to check whether it is properly balanced or not. Whether this load balance index, whatever you are getting in the range of 0 to 1, this minimum divided by maximum means maximum value will get 1 if both are same, right? So you have to check whether this load balance index, it is within a particular range or not. So how to determine that range? For that, they have taken two thresholds. One is phi L, another threshold is phi H. And phi L is less than phi H. Okay. So it maybe looks a little bit complex, but when I tell an example, it is will be more clear. So let us see this example. Then I'll come back to this view. So I have taken two thresholds, 0.2, 0.6. Phi L is 0.2, phi H is 0.6, phi L is less than phi H. Right? That constant we have added. So it is true here. So now, before assigning this set of tasks one by one, so let us assume that the ready time is 89, 73, and 50. What is the maximum ready time? What is the minimum ready time here? Maximum ready time is 89. Minimum ready time is 50. What is phi? Phi is nothing but it is the load balance index calculated is the ratio between minimum ready time to the maximum ready time. Minimum ready time is 50. Maximum ready time is 89. So what value will get? 50 by 89. 0.5. And you have to check these 0.5 should lie between phi L to phi H. Phi L is 0.2, phi H is 0.6. So your value should be in the range of phi L to phi H. If it is deviating this particular range, then your load is not properly balanced. Right? So now, by default, if it is in this particular range, then you will apply MCT algorithm. But when you exceed 0.6 or when you come down to 0.2, you will use MET. Okay, within 0.2 to 0.6, you will use MCT. But if you exceed 0.6 or if you come down to less than 0.2, then you will change your heuristic from MCT to MET. The hybrid algorithm, right? Hybrid means you have to decide whether to apply MET or MCT based on certain conditions. Right? So I am applying MCT. You know, if I apply MCT, I will add 89 with 70, 73 with 80, 50 with 108. Right? So I'm getting 89, 153, and 50 as what? The completion time. Right? Completion time is execution time plus ready time. So I'm getting these three. Now you tell me, out of these three, which one is minimum? Which one is minimum? 50. So obviously T1 is going to assign to No. Out of these, which one is minimum? It is not 50. 70 plus 89, right? 70 plus 89, 80 plus 73, 108 plus 50. Which one is minimum? So if you add, you will get 80 plus 73 is the minimum. You add these three values. I'm getting here 159, right? Sum of these two is 159. It is 153. It is 158. So minimum is 153. Okay. But I have not assigned any task to C1, C3. That's why I'm keeping 89 and 50. You assign a particular task, then only ready time is going to be changed. Otherwise, ready time is same, right? So now after assigning T1, what I have to do? I have to check that whether load is properly balanced or not. So again, I have to take pi. Pi is what? R minimum divided by R maximum. What is R minimum here after T1? It is 50. R maximum is updated to 153. Earlier it is 89. But now it is updated to 153. So what value we are getting here? 0.326. Is 0.326 allowed here? Because it is in the range of 0.2 to 0.6. So it is in the range. So you have to continue your execution with MC. But you will find some case where the value is coming down to 0.2 or it is greater than 0.6. In that case, you will apply MET until unless your value will come to in this particular case. So this is the idea behind the switching algorithm. So if you see switching algorithm case, none of the case you are getting better result, but some of the cases the value is very close to MCT or PT. That's why people also use switching algorithm. Okay, but still the benchmark algorithm is our MCT. Now I'll take another 5-10 minutes. Okay, so this till now whatever we discussed, that is called as online part. Okay, online scheduling. But now we'll come to offline scheduling. What is offline scheduling? If there are 5 tasks are there, the order of their execution is not 1, 2, 3, 4, 5. You can change the order as per your wish or as per the algorithm. So there is a benchmark algorithm that is called as mean, and another is mean. So these algorithms are called as the two-phase algorithm. Previously, whatever algorithm we have seen, that is called as single-phase algorithm, but this one is called as two-phase algorithm. See how we are going to calculate. So if a ETC matrix is given like this, or expected completion time matrix is given to you, first you will find the row minimum. Right? If a matrix is given to you, you find the row minimum. Assume that in the first row you have E11, E12, E1, 1 minus 1, E1n. So out of these, you will find which one is minimum. Let it be E1 alpha. Right? You can find minimum of a particular row. Similarly, find the minimum of the second row. Let it be E2 beta. Minimum of the third row. Let's say E3 gamma and so on. So one page is over. So you are finding row minimum. So a two-dimensional matrix is now divided in compressed to what? Reduced to what? A one-dimensional matrix. It's a 1D matrix, right? Is there one row or one column? We call that is a 1D matrix. Now, in the second phase, what you have to do? You have to find the column minimum. Right? 2D matrix is converted to a 1D matrix. Now I'll find minimum of this particular column. What I will get? I'll get the column element. One element will be get. Okay? That task is going to be executed fast. So for example, if you go for this particular example, 150, 18 in two different machines, 32, 7 for T2 and in another two machine. In that two machine, T3 is another two machines, like 20 and 3. T4 case it is 50 plus 50. Okay, this matrix is given to you. Now find the row minimum. What is the row minimum? 150, 18. Which one is minimum? 18. 32, 7. Which one is minimum? 7. 20 and 3. Which one is minimum? 3. 50 and 15. Which one is minimum? So now a 2D matrix is changed to a single one-dimensional matrix. And what is the next step in phase 2? We have to choose the minimum of the column. Minimum of the column is 3. So T3 is going to execute first. And apply MCT. You know what is MCT. Okay. You can apply MCT. So once T3 is completed, you have ready time. Initial ready time is assumed as 0. Once T3 is completed, this 3 unit of time you have to add to where? 18 plus 3, 7 plus 3, and 15 plus 3. These are the execution times, right? So once a task is completed, ready time will come. So you have to add that particular ready time and execute for other tasks. Once T3 is eliminated, you can see we have added plus 3 in the second machine. You find again the row minimum, column minimum, choose a task, execute. The difference between that, the previous case, you are doing one by one task. That's why it is completely online. Right? But in this case, you have information about a batch of tasks. That's why we need to process one by one. So we can process them in any order rather than going for one by one. Actual cloud environment now, if you see, like we are using IIT BHU Param CI computer. So whenever we are submitting our job, it is in batch only. It is put in a batch. They process in batch wise only. Although one process is they are executing something, but initially they put in a batch. Okay, obviously, whenever we go for online case, most of the cases is online only, right? But offline analysis can also be done, right? There is another case. In order to compare, like speed of factor whenever we are calculating, we do both calculations, scale calculation as well as Palan calculation to know what is the gap, right? Okay, is it clear? Min. There is another algorithm that is called as max min. What do we do in the case of max min? Instead of choosing the minimum value, you are choosing the maximum. Because if you take a data set where there are many maximum values or minimum values, assume that you are taking 5 tasks, all the values are in the range of, let's say, their execution time in the range of 2 to 10. But there is a task whose execution time is more than 100. When small task is more and large task is less, in that case, this large task may dominate the small task. That is the reason why maximum is developed. First, you need to process the last task. Suppose it is dominating in one particular processor, and small task can be assigned to another processor, so that load can be balanced. On the other hand, what happens? Small task is less, large task is more. In that case, min is better. Again, there is a trade-off. Like previously, we have seen a trade-off between MET and MCT. The offline algorithm also there is a trade-off between min and max min. Right? So we can go for max min. I have given different examples so that you can understand. Now people have come up with another algorithm, that is suffrage. Suffrage algorithm says that if your task is not assigned to an appropriate processor or the best processor, how much you will suffer. Right? For example, let us say T0. For T0, which machine is best? Let us call 0, 1, 2, 3 to avoid confusion. Which one is best? C0. Suppose you are not going to assign to C0. Then what is the alternate option? C1, C2, C3 is there. But which one you will choose? Why C1? 48. Yes. 48. So how much you have suffered? 8 units of time. Right? If you are not getting your best option, you will go for the second best option. So you will suffer with the 8 units of time. Like that, for every task, what you have to do? You have to calculate the suffering value. And obviously, the task which is going to suffer most, that we are going to assign. Right or not? So you can see, if you calculate best to machine in the task T1, you will get 50 and 82. So if the best machine you are not getting, then you will go for 82. So your sufferance value is 32. So out of these 4 tasks, you can see T1 is suffered most if it is not assigned to the best machine. So obviously, you will choose T1 first. Okay. So this is the concept behind the suffrage algorithm. I am not telling details. You can go through this slide. So again, I am coming to the same simulation where we have taken the benchmark data set, simulated everything. So you can see in the min case, we are getting 7 out of 12 instances. We are getting better result. Suffrage case, we are getting 5 out of 12. So it is not necessary in the research to show that the 12 out of 12 instances you are getting better result. It is a wrong concept, right? If you take 1000 data sets, obviously your algorithm may not perform well in certain data sets. So that you can see. Once Min is developed, people have developed separates. Still, that paper is accepted in a very good journal, right? What they did? Only 5 instances, but you can see 1, 2, 3, 4, 5. These are the 5 unique instances where they outperform than the Min algorithm. Okay. So in this way, you can define online algorithm and offline algorithm and execute in multiple processes. So what is my advice is that whatever programming language you are learning, or today also you see CUDA, to try to implement this with the real environment. Obviously, we are doing it with a simple environment, but do it with the right to OpenMP code or API, and execute these applications. Okay, by creating actual machines. If you can do it, then it is really good. Okay, we'll stop here because we don't have time. If you have any question, you can ask.